Yeah, there we go.
Ah, there we go. All right, very good. All right. So Professor Thomas is on board. He's got his speakers on board. So I think we are 3 minutes ahead of schedule. That's interesting. So we leave it to Professor Thomas to take it from here, please.
Okay, so it's my pleasure to invite Professor Kistryn to talk to us. I hope.
Yeah, Professor Kistryn, you are the co-host.
Okay.
You should be able
to Thank you. I am, well, now I can unmute myself. Thank you very much. Welcome, everyone. Good morning, good afternoon, or good evening, depending on your time zone. So I am very grateful for the organizers to invite me to this prestigious lecture series commemorating Professor Mitra and all late physicists who were mentioned at the beginning at the introductory talk. So let me dedicate this talk, and I hope that my colleagues will also do it for to all the memory of the great physicists, our colleagues who passed away already. But I think as still alive, we will enjoy things here. So I will try to share my screen. I think it is there, and I think it might be also shared as a PowerPoint. Yes, so my task here is to tell you the view on three-nucleon system dynamics from the point of view of an experimentalist. So I will be talking about what I call, with your permission, new generation of experiments, which at present are rather present generation experiments, but when we introduced them, they were new, so let me call it like this. And the other disclaimer at the beginning is, of course, I will be showing several examples of the different effects in three-nucleon system. But of course, I am not claiming that I know everything. I will be mainly using the results of my group, but also of other groups which are known to me. And the last point is that, well, I will start from the very basic things. So I am apologizing to everyone who knows that already, but I wanted to prepare somehow a full, coherent story, let's say. So let me start from this beginning. We know a lot about nucleon-nucleon potential, about the nuclear force. It has been established, as Indrani was saying in the beginning, in some details. I show you here 3 approaches to it. All of them are based on the Yukawa model. The force is mediated by exchange of mesons. And in so-called realistic potentials, semi-phenomenological potentials, a lot of mesons or well-correlated exchanges are allowed, forming, the potentials like Bonn or Argon I will be mainly referring to. A bit of extension is a coupled baryonic channel approach where one allows 1 degree of freedom of 1 delta resonance. Again, the force is mediated by the exchanging of mesons. And perhaps more fundamental approach is effective field theory, here called chiral perturbation theory for the sake of nuclear physics, where the potential is expanded in a series of, small external momenta. Here we have the pion exchanges and the high energy or low distance physics is coded in contact terms characterized by low energy constants. Those approaches are very successful. They can very well reproduce the bulk of two nucleon interaction data, not only binding energy of the deuteron, but all the scatterings observables, cross sections and polarization observables with very high precision, depicted here as a chi-square per point, which is close to 1 for all those potentials. If the situation is that good, we should use those potentials for the, what I want to talk about is the three-nucleon system, or rather for many nucleon systems, since we want to reproduce also heavy nuclei and their reactions. So the least complicated system is the system composed of three nucleons. So let us test the models in this small, really small system. Of course, you all know that with investigating the scattering observables, but also other effects in nuclear physics, it has been found that just nucleon-nucleon force is not enough, and that led us to introducing the irreducible genuine three-nucleon force, which now we know that exists, but we want to pin down its details. Of course, I will be talking more about the evidences in a moment. Now let me just shortly mention what is this three-nucleon force. Obviously, we know that proton is not elemental, is not fundamental as a particle without structure. It has its internal structure. In fact, we teach students that it is composed of three quarks, similar as a neutron, but in fact we know that the picture is much more complicated. There are gluons and quarks interacting inside the nucleon. However, even if we stay at this valence quark picture, we can explain the interactions, these exchanges of mesons between nucleons as a rest potential, rest force of a really fundamental strong interaction between quarks and gluons. And since we are neglecting internal structures of the particles we take as a fundamental, we need to include some effective forces, and these are these many nucleon forces. Those are, of course, can be also modeled. I show you here the pictures of models of three-nucleon forces in usually coupled with realistic potentials are also semi-phenomenological forces like Taxon Melbourne or Urbana force. In coupled baryonic channels, this existence of delta and simultaneous, let's say, or consecutive exchange of pions between all three nucleons leads to appearance of three-nucleon forces, or the delta-induced forces, which are competing with the graph on the left, which is the nuclear dispersion, which I mean here, and in chiral perturbation theory, in this systematic expansion of the potential, at the next to leading order, there appear first contributions, which we call three-nucleon forces with three possible topologies. I am sure that my colleague Roman can speak much more about this. I am plain experimentalist using the wisdom of theorists to compare our data with theory. However, to compare really those two approaches, experimental and theoretical, we need tools, and those tools which transport directly the assumptions, dynamical assumptions coded in the models of potentials to the calculated observables. And Indranil in his introduction mentions this tool. These are Faddeev equations. However, to solve numerically exact rigorously this Faddeev equation, you need really to work hard. and that has been for the first time, well, quite a few years ago, proposed by late Professor Glekle and Witała, the Bochum Kraków group. And then these approaches has been widespread, and we can now really say that what we calculate is really corresponding to exact dynamics we assume in the potential models of 2 and 3 nucleon interaction. I just wanted as an experimentalist to impress you that I can understand Faddeev equation once I really understood how they are constructed. I do not claim that I know how to solve them numerically. That's the job of my colleagues. Now, just to show you and remind you the action of 3-nucleon force, including 3-nucleon force in 3-nucleon system, only with the use of those 3-nucleon force models, we can properly reproduce binding energies of 3 and 4 nucleon system. We can reproduce also some level sequence of light nuclei. I will not show more about these observables. It is also important to correctly reproduce the nuclear matter equation of states, many other observables. I will be talking about scattering observables in 3 nucleon systems. I cannot, however, resist to show you one very important thing, this famous Hoyle's tail in carbon-12. Only with inclusion of 3-nucleon forces, the correct sequence and approximate positions of the states in carbon-12 with this important state for star existence and star burning, it can be properly reproduced. So we know now that the 3-nucleon forces are important, and let me demonstrate this importance also for the scattering in few nucleon systems, in essentially 3 nucleons. Well, attacking 3 nucleons, we have usually starting with a deuteron and a nucleon, and we have 2 main channels, elastic scattering and breakup channel. The breakup channel with much richer final state, which is also very important. And we have different observables with different effects to be studied. Not only the details of 3-nucleon forces, but also the long-range Coulomb interaction effects, relativistic effects, and what is perhaps most important, also the interplay of these different pieces of nuclear dynamics. When starting from with elastic scattering, nucleon-deuteron elastic scattering, we have essentially 2 experimental techniques, either large acceptance detectors with coverage of large phase space at once, but with moderate resolution usually, or high resolution spectrometers on the cost of experimental acceptance. I will talk a bit more about experiments in the case of breakup. Now I wanted only to flash it. Now, this is the most, let's say, spectacular picture we were always using as demonstrating the action of 3-nucleon forces in elastic nucleon deuteron scattering. When you see that calculations based only on 2 nucleons are underestimating the cross-section in its minimum. It's at here as example energy of 100, almost around 100 MeV per nucleon. When including 3-nucleon force, this minimum is nicely filled. However, when we look at the analyzing power at the same energy in the same reaction with polarized nucleons, we see that simultaneously this 3-nucleon force is a bit, one can say, does not help or even deteriorates agreement in the minimum or let's say maximum, absolute maximum of the analyzing power. So it points at some problems with the models of 3-nucleon force still. More systematic studies have been performed on this effect. Here, if we look at the cross-section in its minimum and departure from the purely two-nucleon based calculations, we see that when we use only calculations based on nucleon-nucleon force, the differences between experiment and theory in this minimum, depicted here by these vertical violet lines, can reach at higher energies, higher, I mean 200 MeV per nucleon, of about more than 100% difference. When we include three-nucleon force, this discrepancy is reduced. However, it is not completely removed. Here, at this higher energy, it is the improvement is by factor of 3, but still there is something to be accounted for further. When we look at polarization observables, the picture is not also not quite clear. Maybe let me look at show you another example of tensor polarization. If we use polarized deuteron beam, we can study also tensor polarizations. And if you look here at the right picture, you see completely different behavior of data with the energy of not big range, but still, and theoretical predictions. At lower scattering angles, the data are quite well reproduced with only two-nucleon potential predictions, and they do not depend very much on energy, whereas the predictions are showing the energy dependence, and they are not following the data. At higher scattering angles, to the contrary, the predictions of different energies with three-nucleon forces are quite agreeing at every energy, but the data show dependence of with the energy and quite strong. So it means that we still are missing something in the models of three-nucleon force, or generally the interaction. Here I show you the results of our Japanese colleagues, also not so new, but still very accurate measurements at different energies, showing, as we were discussing previously, mixed picture. The rough structure of data is reproduced for virtually every observable, but the details are not, and that means we have to look at it more closely. In fact, we could think that might be there is some Coulomb interaction or relativistic effect involved. However, the predictions, the calculations show that for elastic scattering, the effects are rather very small and concentrated at extreme angles, so they cannot account for all these discrepancies which we still have between the data and the experiment. This small effect of Coulomb force was for a while misleading. We were expecting that also in breakup case, the Coulomb interaction might be quite not important, and it is good because when you treat the Faddeev equations, it is quite complicated to include long-range forces. So usually the calculations were performed, at least at the beginning, for the neutron-deuteron system, whereas experiments are much easier when you use protons and deuterons, and when you can register charged particles. But before passing to further, let me show that the database for elastic scattering in proton-deuteron and neutron-deuteron-less is quite abundant. We have a lot of observables measured and different energies below pion production threshold. However, the picture, as I showed you, it's not quite clear. Therefore, let us use also a more rich final state of nucleon-deuteron breakup to show, to look how the theories can reproduce the data. Now, in the breakup case, just a short reminder, as we teach the students, we have to measure two particles in the exit channel to completely reproduce kinematical configuration, that is directions and momenta or momenta vectors of all three particles. Well, conservation laws impose 4 restrictions on the variables in the exit channel, so we need to measure at least 5 remaining. Usually, when in the case of, well, let's say registering 2 protons, as is in this picture, you usually register the directions, that is 4 angles, and energies, and that over determines final state. So for selected angles, polar and azimuthal angles, your results, your data should lie along the so-called kinematical curves, and we parameterize and use the to avoid ambiguities which might arise when we use energies. We use the so-called arc length variable, which is, well, depicting the data along this variable, which is starting at the minimum usual of this kinematical curve. So it's for convenience we use this variable, and that will be shown in my further talk. Well, now let me spend, since I am experimentalist, I must show you some experimental setups. The first, what we call the new generation experiment, and this new generation was covering large piece of phase space at once, not just placing, well, a few discrete detectors on both sides, usually on the beam or up and down, and measuring asymmetries in the case of polarization or cross-section and summing up. We have decided to use an existing system when working with our colleagues at KVN in Groningen in Netherlands. We came to the idea to supplement the system called SALAD, which was consisting of the wire chamber and 6 scintillator hodoscope, which was used for Bremsstrahlung experiments, of course, together with a photon detector setup, to supplement it with a set of hodoscope of thin detectors, which allow us to identify protons and deuterons. And in that way, we could use and we could determine at once a lot of kinematical coverage. We can realize a lot of kinematical coverage. I am not going into the details of the system. It was our first and very successful usage of such a let's say coverage of large piece of phase space. It was so successful that we decided to upgrade it, and the upgrade was called BINA, Big Instrument for Nuclear Analysis, again at KVI Groningen, implemented. The forward wall composed of the scintillator hodoscope of thick and thin detectors, and wire chamber is quite similar to the SALAD detectors. However, we covered the backward, or well, quite the rest of the phase space with 150 phosphate detectors, which simultaneously built a vacuum chamber in which the target, liquid target of hydrogen or deuterium has been placed. And in this way, we were able to cover almost 4 pi for the breakup reaction. Another system is quite different. We decided, for the sake of measuring very small scattering angles, a small detector, you see, of the diameter of a few centimeters has been used in another laboratory in Jülich, using the external beam from the COSY COSY accelerator. We used COSY could produce GeF proton beams, but we used usually only a few hundred, or essentially in this experiment only 100 MeV, 130 MeV beam. However, with this highly segmented detector, essentially this front Chiral detector with 200 spirals, we could again have the very good position resolution or tracking of the protons from the reactions, and with the SIG detectors determining exactly the energies. I will show you why we use it and what provided these detectors. We used also the regular internal COSY beam with the WASA detector, usually used for high energy physics experiment, so the calorimeter to measure essentially all. We used only essentially the forward wall when we studied our breakup reaction at really higher energies of, let's say, 200 MeVs. So let me boast that with those setups, we were able really to, in one experiment, to provide quite a lot of data. I mentioned, and we did it also previously in Groningen, in Switzerland, at PSI at that time, a number of experiments with discrete detectors measuring proton-deuteron breakup. And usually we had at hand, well, perhaps 6 or 8 kinematical configuration measured with one setting. Here at once, so the 6 configurations or 8 were, say, 100, 150 data points to in one shot. Here in a single experiment, we were able to provide 2,000, so an order of magnitude more data. Also for polarization observables, when using deuteron beams, you have an access to a number of vector and tensor analyzing powers. Similarly, for the small detectors, this germanium wall I showed you, it was also the case that we could have provided really thousands of data points, which is quite a number to test predictions of different theoretical models. So here I also can show you what our full experimental programs, which is partially completed and partially going on in Kraków, with BINA detector being well taken from KVI after it closed its part, this part of the physics program. We have measured a lot of cross sections at different energies, also partially covering polarization observables. So examples. The first, well, we were able to determine the importance of three-nucleon forces in breakup. That was shown for different configurations. Those calculations which are shown here, were for different, not for this. You see here we have, I have selected the very small emission polar angles with different azimuthal angles. When we go to higher polar angles, the data are very nicely reproduced with this, well, including three-nucleon forces. And the three-nucleon force effects are not large, but they are bringing data, the calculations closer to the data. However, at small angles, we have established a number of discrepancies, and we were very suspicious that perhaps we are close to our acceptance with salad detectors. So perhaps we are missing here something. And only after the group performing calculations within this baryonic coupled channels models or framework was courageous enough. So Antonio Fonseca and Arnaud Studa were the first to include long-range Coulomb interaction together with the delta effects, that is three-nucleon forces, and that was, well, quite an astonishment that Coulomb force effects in breakup can be quite large. Well, if you think now, it is obvious. Well, if you have a pair of protons which, well, when flying together, so emit when they are emitted together with similar momenta, which is the case in this maximum of cross sections with at small angles, they interact obviously. So, well, when we determined that, it was quite something which we were well quite proud of, that both theorists and experimentalists come to agreement with some not so expected effects. And that made us to perform this experiment with the very small emission angles, with germanium wall detectors, with still smaller polar angles. You see that when you select really protons flying together, the cross sections is not only suppressed from the predictions with 2 and 3 nucleon forces, but it is distorted, creating even a minimum in the central part of this S curve, and only Coulomb introduction can make this. And I can make this data to correctly reproduce. To show a global analysis, let me show the following picture. When we take all our data it was at 130 MeV of the deuteron beam, so 65 MeV per nucleon. When we compare our data we integrate our data over all variables but relative energy of the 2 protons of the outgoing channel. By the way, this relative energy is well, one of the very useful variables, because it is kind of well, if you can use it at different energies of the beam, whereas comparing data for breakup at different beam energies or the available in the center of mass energy is quite difficult. Here you can do this comparison easily. However, let's look at one energy. When we integrate out all our data but with respect to this relative energy and compare experimental results, these are in fact 5-fold cross sections with theoretical predictions and relatively to the, let's say, experimental value, we can see that the data are quite strongly overestimated at lower relative energies and underestimated at higher relative energies. Including of 3 nucleon forces improves the picture at higher relative energies. Well, at low energies, one could claim that this agreement is even worse a bit. For a change, if you include to the 2 nucleon potential here are gone only Coulomb correction, Coulomb interaction, you see that the picture at higher energies is not altered. The Coulomb force does not change the agreement or the disagreement at the higher angles at all, but at the forward, not angles, but larger relative energy, the picture is not changed. However, at lower energies, the agreement is quite improved, lower energies. So, and the conclusion was that only including both effects, 3 nucleon forces and Coulomb interaction, can bring data and calculation, theoretical predictions quite close together. So it is not only important to think about one dynamical effects, but in fact, to correctly reproduce data, you need to include all your best knowledge, that is all the effects which can play a role in such a complicated system. So let me just quickly show you other examples which will tell you that at a bit different energy, no, not a bit different, twice larger energy at 135 MeV per nucleon in the proton, with the proton beam. You see that there are configurations where Coulomb effects can nicely reproduce the data. There are configurations in which 3 nucleon forces are bringing calculations closer to the data, and there are configurations in which none of the predictions, theoretical predictions, can correctly reproduce the data. So here still we conclude that we are still missing some dynamical ingredient which is important at this particular configuration of the breakup reaction. That can be confirmed also in other another set of data, but let me go now from cross sections also to the polarization observables. Here one can see the full power of this new generation or present generation experiments when you cover a lot of phase space simultaneously. That is when you measure when you select certain set of polar angles and relative angle between, say, two protons, then you can then rotate this configuration around beam axis or around the polarization with respect to the polarization. Then this big phi will tell you the angle between the configuration plane or whatever the configuration and the polarization. And then you not only measure asymmetry, this asymmetry is generalized, and this combination of sine and cosine function is nicely reproduced. So you can by fitting that function, you determine all those polarization parameters, let's say, or polarization observables, and you have much better control over systematic effects. So covering big pieces of phase space has not only advantage of increasing acceptance, but also making the polarization determination much more not only easy, but also much more reliable. You can check this reliability by taking, for instance, parity symmetry, which requires that certain observables are symmetric or anti-symmetric when you change the protons or final nucleons in a pair. When you interchange them, for instance, this AX should be anti-symmetric, and when you really determine your experimentally, or for instance adds it, you see that you have the proof that your quite well indication that your experimental setup is really symmetric and that you can guess about the absolute value of analyzing powers. So when we look at the general picture of what we measured, again, let's say at 130 MeV of the deuteron beam with polarized deuteron, the different colors depict different analyzing powers, again, integrated over all our data set, and the relative difference between the predictions and the experiment for different analyzing powers, including different pieces of nuclear dynamics. One again sees that, for instance, AY is not really sensitive to any dynamics and is correctly, more or less correctly reproduced with every theoretical model. However, there are observables like this tensor polarization and AXX, which is not so correctly reproduced by any theoretical description, and with whatever you include, Three-Nucleon force or Coulomb interaction, this discrepancy between data and experiment is quite large. And there are some strange effects like this in AXY, that including, for instance, Three-Nucleon force to the two nucleon models, suddenly introduces quite large discrepancies when you look over the whole data set. Of course, you can take now the specific configurations and look where those discrepancies occur. What is also something when you make this more detailed analysis, you can see that the deviations are, well, what I call anti-phased. When you look at cross sections and where you experience large deviations from any calculations with the experimental data, then the analyzing power is pretty nicely reproduced. And when you, for a change, when you look at the configuration, where the analyzing power shows deviation between experiment and theory, then the cross section is quite well reproduced, at least in these lower values of relative azimuthal angle. So again, it shows you that we have some mixed picture, and still we should work on models of the nuclear dynamics to reproduce all the data. Maybe I will not discuss more about that. I wanted to only to show you that this more recent data published more recently also show some deviations like here, which can be cured, or some cannot be cured. I also want to well praise our Japanese colleague who performed very complicated experiments with double scattering, measuring polarization, induced polarization and polarization transfer coefficients for breakup. It is really very hard experiment. Therefore, the data are pretty scarce. Some calculations seem that again roughly the data can be reproduced, but in the case you have 1 point of data, you cannot say much. And that is well calling for more work also on the experimental side. The database established well, or even I can say established worldwide with our strong contribution to fill all these gaps is much less abundant than for the case of elastic scattering. We have quite a lot data for cross-section, but polarization observables are, well, essentially quite rarely addressed, and they are really very sensitive to details of nuclear dynamics and should be studied in more details. What I also mentioned, we are also working to to represent the results not in our, say, laboratory convenient observables like emission angles and energies or momenta, but more invariant variables, what would enable us to perform comparisons, easier comparisons between different available energies, that is, between experiments performed at different energies. For the elastic scattering, well, you can go to the center of mass, and then the comparison is not anymore a problem. For 2-nucleon data, you have phase shifts which you can use for comparison. For the breakup case, we always have this problem, what we should really compare, what configuration at different beam energies should be compared with which one at another beam energy, and that is for our work in progress to transform it to the invariant variables. Approaching the end, I would like to show you that we also would like to pass to more complicated system and test our the available calculations in 4-nucleon systems. Some very first calculations were for elastic DD or breakup DD were showing well. They were really very first ones, so perhaps not look at them. If we take some more recent calculations and predictions, well, one can say that we again can understand this system with the present state of art of the calculations, and so perhaps this system would be very good to study also the nuclear dynamics. Naive intuition says that that effect of three-nucleon forces should be enhanced in four-nucleon systems, since you have more this combination of three nucleons with respect to, well, just pairs than in the three-nucleon system. In three-nucleon system, you have three pairs and one triples, and whereas in four nucleons, you have six pairs available and three and four this three nucleon configurations or systems. So at least by factor of 2, naively speaking, the effect of three nucleon forces should be enhanced. And we have tried and we will try to continue those experiments. Maybe I will skip that. Just going slowly to my summary. I tried to show you the experimentalist view on what we know about three-nucleon or few-nucleon system, that a lot of data which is available is giving us basis to test very strictly the models of nuclear dynamics which our theoretical colleagues are providing. We have showed together that there are that importance of three-nucleon forces also in the scattering in few-nucleon system is really that it is really large. That we have found also different influences of different effects like Coulomb forces, and in specific configurations also relativistic effects, which I have not been showing, but please believe me. And the importance is that we really, to compare the data with theories, we either look at the configurations which we know that they are sensitive only to certain pieces of nuclear dynamics, or that we include in predictions interplay of all important aspects of the three-nucleon force dynamics. The general picture is not very clear. It calls for further investigations, both on the side of theory and experiment. And just let me show, maybe I will go back since I have a minute or two. I tried to look, to provide you also with some references for recent reviews of experimental works. However, I have not been able to find one. Instead, I show you the very recent publication in few-body system, which has some quite a number of references to also experimental works, and I just recognize that maybe experimentalists should also try to summarize what we know already since our last review. It's already some more than 10 years, so perhaps it would be good to address this also. My wishes or my view, what are the prospects? So of course we have still there are always problems with manpower, so we are still working on analyzing our data sets accumulated in the past. We are working on this new approach to breakup analysis with new set of variables. I am not sure whether more data on breakup or on four-body system will come from other labs, but at least in Krakow, after acquiring this complicated BINA detector from KVI, we are continuing our experiments. For instance, we are planning to study neutron-proton final state interactions, measuring also neutrons to confirm that we can, what are the differences between proton-proton and neutron-proton pairs in the final state. And we want to study induced polarization in the proton-neutron breakup to also address polarization observables. For that, we will supplement this BINA detector with what we have, with our additional wire chamber and scatterer analyzing the polarization. We want to take the challenge of double scattering experiments. Also, in the on the side of theories, there is strong progress. I am sure that Roman and Alejandro will tell more about that. But well, there is a progress in chiral perturbation theory, including higher and higher orders of calculations, and also including deltas, including Coulomb interaction more exactly, and well, also addressing 3-4-nucleon system with exact solution of the Jakubowski equations. So my final word is I took advantage to present the same slide as I was using 15 years ago when Indranil introduced me to a workshop in Mumbai. Well, saying that in my view, few body systems still remain attractive ground for studies nuclear dynamics, and one is well justified to study them both experimentally and theoretically. Thank you for your attention.
Thank you very much. Now, I'm not sure whether I haven't seen any questions on the chat line. So if there are questions, I guess the best way is to react by raising a hand. If you look on the bottom of the screen and choose react. Yes, Drano.
Yeah, thanks, Tazek, for, again, a terrific overview of the subject. I have some general questions, like this is the first one. This is very close to my heart, this AY puzzle. As a seasoned practitioner, I want something decisive, because many people these days say, oh, no, it's not really that much, when I try to sell the subject by talking about the incompleteness of the AY puzzle that is not yet resolved. So please give your comments whether it is still worth it, or it is just a matter of some more statistics and fine-tuning the theory.
Yeah, well, thank you for the question. I must say that I had a slide with the AY puzzle also, but I removed it from the presentation. As far as I know, the puzzle still exists. And it is not only that, it is this low energy AY puzzle. I showed you that it can be extended also to higher energies. And I am sure that Roman and Alejandro can tell more about possible explanations, like the contribution of P or D waves in the calculations. However, I think that the problem is quite essential, and we should. Of course, it is present in the elastic scattering, so it is even more fundamental than in the breakup, where we can always say there is some more problems appear. However, I think that we should treat all those puzzles which I tried to signal, and there are certainly more, to treat them simultaneously, because we will be able to say we understand what is the dynamics of three-nucleon system only when we correctly describe everything: the AY puzzle at lower energies, the scattering at the breakups at higher energies, also perhaps this polarization observables at higher energies, and nuclear equation of state, for instance, which is also a problem. Also states of light nuclei, like perhaps not going even to beryllium, but let's say lithium at boron. When we can from scratch calculate them with our models of 3 and 2 nucleon forces, we say, well, we know how what is really in nature, what the nature gave us as an interaction. So sorry for not addressing details of AY puzzle, but I think that I am not at the moment competent to tell what is really at present the situation.
Okay. Thank you.
Next question is Professor Mitra.
Okay.
Hi. I just had a quick question. Though I'm not familiar with this particular area, but I used to work in chiral perturbation theory about more than 27 odd years ago. So isn't the following true, that there are some convergence issues related to use of chiral perturbation theory or heavy baryon chiral perturbation theory at N3LO, etc., when dealing with these proton, neutron, neutron, deuteron breakup reactions?
Well, I think that you should, sorry for that, you should wait for this question for the talk of Roman. He will be certainly more competent to answer that. What I know well from colleagues with theorists with whom we are working, those issues were overcome by certain introduction of certain procedures in the theories, but I am sure that Roman will be more competent to answer that. I am plain experimentalist of just comparing the data with what I am getting. Yeah, not just exaggerating, but the details will be much better explained by the theorists themselves.
If I may, firstly, the impressive calculations and experimental results. I had a question that maybe is a little more fundamental, perhaps. We know that the three-body force is not unique. If you change the two-body force, the corresponding three-body force will not be the same. So what is the source of the three-body force being used in the calculations you showed? To what extent are the parameters of that three-body force adjusted to fit the data? And particularly when it comes to spin-dependent forces, are there parameters describing the spin dependence of the three-body force?
Thanks. That's really something which is really very important. That's why the three-body forces are usually the models in the semi-phenomenological approaches are tuned to specific to nucleon potentials, as you rightly point to. So therefore, there is combination of Bonn with taxon Melbourne and argon with Urbana, because they are kind of tuned. So the parameters are adjusted. I think that the most relevant and most fundamental approach of chiral perturbation theory were essentially when you add these higher orders, at least perhaps at N3LO and N2LO, you have just two additional parameters which enter in these 3 graphs. There are only the two additional low energy constants which you adjust to some binding energy and scattering lengths, and all others all other observables should be correctly displayed. So the three-nucleon forces usually inside they do not have too many additional parameters when you compare these 40, let's say, parameters of nucleon potential. However, this tuning must be done, because otherwise they do not fit. But in the case of chiral perturbation theory, at least as far as I can be expert in the theoretical field, as an experimentalist, this comes quite let's say, model independent, in the sense that there are this expansion follows certain rules and requires in higher and higher orders to fit only a few additional constants. I am not sure whether I have answered your question, but perhaps again I will refer to my colleagues to better explain it after they talk on the theoretical side.
No, thank you for that. The one comment I'd make is that the assumption of chiral perturbation theory is the short distance force is local.
Yes.
And we know if you make unitary transformations which introduce non-locality, you can change the results substantially. But I should stop talking. It's my job to chair. So are there any other questions? In that case, thank you very much.
Thank you. Thank you very much.